MATCON 2021. This session involves an invited lecture and 7 oral presentations. I invite Dr. Sebastian Nabil Romello to chair the session. Dr. Romello is the Assistant Professor of Department of Applied Chemistry, CUSAT. His research interests involve artificial photosynthesis, metal complexes, electrocatalysis, and photocatalysis. Please, sir.
Thank you, Golda. So, I thank the organizers for giving me this opportunity. So, first let me introduce Professor Biprajit Sarkar. It's indeed an happy occasion for the Department of Applied Chemistry, CUSAT, to have Professor Biprajit as one of the invited speaker for the MATCON 2021. Professor Biprajit Sarkar is currently a professor at the University of Stuttgart, Department of Inorganic Chemistry. He is also the director and chair of department. Before joining University of Stuttgart, he was a professor at the Free University of Berlin, and he did several postdocs. He was a postdoctoral researcher at the lab of Professor Braunstein at the University of Louis Pasteur, Strasbourg, France. Then he did his PhD with Professor Wolfgang Kehm, who is a very known person for the Department of Applied Chemistry at the Institute of Inorganic Chemistry, University of Stuttgart in 2005. So before that, he did his MSc from IIT Mumbai, and he did his BSc from University of Calcutta. So it's his main area of research is his main area of research is electron transfer and optically switchable molecules with non-innocent ligand, mesoionic carbines and their catalysis. Then small molecule activation. I hope he will talk on CO2 reduction, water splitting aspects. Then, and he also received several awards, prestigious ones. He is selected as the Rising Stars at the 41st International Conference of Coordination Chemistry. He also awarded the Sashikai Lectureship of the University of Tokyo. Then he is also instrumental in bringing about MOU with several Indian institutes. So I hope we will have a very interesting and engaging session. With this, I welcome Professor Biprajit Sarkar to deliver this talk. Welcome, sir.
Okay. Thank you very much for inviting me, of course, to this conference. And I have to apologize for not being a very good conference participant. Let's say these days have been rather busy here. So I basically, this is the first time I'm logging in. So my apologies for that. Do you see my screen now?
Yes, sir. Yes, sir.
Okay. So basically, I will talk about mesoionic carbines today, and as we progress in this talk, hopefully it will become clear what I'm trying to say, or what I will try to say. So some fundamental aspects and then some applications of this. So this virtual format, who knows, maybe this is the new normal. So virtually I'm in Cochin today, kind of strange because I think outside here the temperature is probably +3, and at your place it's probably 30 something at the moment. Anyway, so let's see, these are some topics. This was already mentioned in the introduction that we work on in our group. So magnetically and optoelectronically switchable molecular materials. small molecule activation. So I will talk about two of these aspects today. Catalysis of various sorts, usually things that are stimuli responsive. So basically catalysis that you can start on and off by using an external stimulus. And we also do some work on metal complexes for medicinal purposes, but this is something that we do in collaboration with other groups. So we are basically making the compounds in that case. Okay, so here you see an overview of some other topics that I will not talk about today. So we do a lot of work on macrocyclic ligands. So this is something I will not discuss today. Also on these typical redox active ligands, azo-containing compounds, quinones, and so on. On triazoles, this is another large field in which we are involved. But as I said, today I'll talk about mesoionic carbines, and in particular, these aspects. So donor properties, CO2 reduction, H2 production, some photochemistry, and then towards the second half, I'll talk about redox switchable catalysis and anionic mesoionic carbines, and then concluded by telling you what we have done until now and where this field should go. Okay, so let me just start by introducing you to these 1, 2, 3 triazoles, because these would be, or these are the precursors of the mesoionic carbines that we are using. So a very small heterocycle, just 5 members, but a fairly powerful and interesting one in our view. The reason is, if you look at this from a coordination or organometallic chemistry perspective, then of course this is a donor atom for a metal. This is also a donor atom for a metal. You can alkylate here. That will be important for making the carbines. Both of these can work as hydrogen bond acceptors. If you think about making supramolecular assemblies, you can tune steric and electronics at both these places, because the variation that you can have here is actually unlimiting. And you can introduce additional donor atoms here and here, and then make up multidentate ligands. And this hydrogen atom here, you can also deprotonate it in the neutral state and then make an anionic ligand. More interesting, however, is if you alkylate here, make a trizolium salt and deprotonate here, which would be the carbene. And these carbines are the ones that would form the main part of my talk today. So just a brief introduction to carbines. So carbines as fleeting intermediates in organic synthesis, this is of course known for more than a century. The first people to point out that these N-heterocyclic carbines can work as ligands were probably Wanslik and Oeffele at Munich in Germany at the time. But a real big breakthrough came through the isolation of this particular carbene with elemental substituents here from the group of Arduengo in 1991. So this seminal work where they showed that this carbene is now no longer fleeting as these ones, but you can actually isolate them, crystallize them, store it in the bench for months without any decomposition. So this then opens up, of course, various fields of chemistry where you can use this for whatever purposes you might want to. And then, of course, there has been many modifications based on these carbines, either the substituents here or modifying the backbone and so on and so forth. So another breakthrough in this field, this appeared in 2001 when the group of Crabtree showed that normally this is where the carbene would be, but if you deliberately block that position, so the so-called C2 position of the imidazolium, then the system will be forced to get deprotonated elsewhere. So here, for example, and then you generate these intriguing molecules where if you try to draw Lewis structures, you have no way to do this without making a formal charge separation. So if you follow octet rules and so on, and hence the name mesoionic carbene stuck to these kinds of carbines. So this is where mesoionic carbines started from, at least in recent times. So these are not the ones that we are working on. So we are working on these mesoionic carbines. As I told you, triazoles, I showed this to you 2 slides back. These can be made very efficiently through this so-called click reaction, copper catalyzed azide alkyne cycloaddition. And once you have this triazole, you can alkylate this at the N3 position, make a triazolium salt, and then deprotonate that CH proton to make carbenes. These are also mesoionic carbenes, now not based on imidazole, but based on triazole. So 1,2,3 triazole 5 ilidenes. So these are the mesoionic carbenes that we work on. So here again, a brief overview of how to make these carbenes. So the cycloaddition reaction, the thermal version of this is of course very, very old. This is more than a century old. And people like Huisgen in the 1960s, they systematically studied or did a lot of work on this thermal reaction. However, in the thermal reaction, you always produce a mixture of two regioisomers, as you see here, the so-called 1,4 and the 1,5 regioisomer. If you do this in a catalyzed way, and that is where people like Sharpless, Fokin, and so on came into the picture in early 2000s. So in the copper catalyzed version, you exclusively make the 1,4 triazole, as I already showed you, and you can do another kind of catalysis, so either metal-free or ruthenium catalyzed, and then you make these 1,5 triazoles. So basically, for these kind of triazoles, you would alkylate here to make the triazolium salt, deprotonate here to make the carbene. So this was already known before we started our work. And what we introduced is, if you take these 1,5 triazoles, 1,5 regioisomers, you can alkylate here and deprotonate here and make a carbene again, with the slight advantage that you can do late stage functionalization here, because that nitrogen is ortho to the carbene that you would generate, and hence would have a much larger influence on the properties of the carbene than the alkylation here would have. So this is what we introduced, but as I said, we work on both these type of carbenes for our work. So let me give you a brief overview of basically the width and breadth of ligands that you can generate by this method. So all based on carbenes, of course. So this is a simple monodentate carbene, something that we have been seeing now in this past several slides. But then, of course, you can make chelating carbenes. So a bicarbene with a spacer, pyridyl carbene, another type of pyridyl carbene. You can also make these ditopic and tritopic ligands, very useful for generating supramolecular assemblies. And what we recently established in collaboration with the group of Koshmal in Ljubljana is this kind of carbenes, where you do not alkylate but arylate the backbone. And the advantage is, if you arylate this, the lifetime of the free carbene is much, much higher than it is here. And so you again get access to several other new types of chemistry. So these are neutral carbenes. We can also make cationic carbenes. And if you look into the literature, cationic carbenes are extremely rare. And these are now a well-established set of cationic carbenes that we established in 2015. So based on a ferrocenium backbone here, or based on either cobaltocenium or a combination of cobaltocenium and ferrocene, or cobaltocenium ferrocenium. With these carbenes, so first of all, they are cationic, but you also have the advantage that because the substituents are redox active, I mean, the redox chemistry of ferrocene is, of course, very, very well established, the ones of cobaltocene as well. So you have the chance of tuning donor properties reversibly through redox processes on the ligand periphery. So that's where these carbenes become interesting. And I will show you one or the other example where these properties can be used. What we most recently introduced in this field are these anionic carbenes based on a borate backbone. So in this case, again, you can either have bidentate carbenes or tridentate carbenes based on such a borate backbone. And what we observe for these bidentate carbenes, and this is what I will show towards the end of my talk today, are these isomerization reactions. If you just focus on this part, where a BN bond isomerizes to BC bond, and you can have this isomerization either on one side or on both sides, as we will see later on. Now, these anionic carbenes are, of course, extremely valuable ligands for doing small molecule activation, and these ligands you can only make through the 1,5 triazole route that I showed a few slides back. So that's where the synthetic utility of this 1,5 triazole route becomes obvious then. Okay, so in the first part, I will talk about neutral chelating mesoionic carbenes. a bit on donor properties, then electrocatalytic CO2 reduction, H2 production, and then a bit on photochemistry of these ligands. Okay, so in one of these work that we did 2-3 years back, the idea was if we compare a large series of ligands where we take bipyridine as the archetype, because this is very, very well established, of course, and then successively change either one pyridine for a triazole, or change both the pyridines for 2 triazoles, or change one pyridine for a carbene, or make it 1 carbene, 1 triazole, or make it 2 carbenes. How do the donor and the acceptor properties of these ligands change? We also used various substituents, as you see here. And for establishing donor acceptor properties in this case, we basically used this rhenium-based platform, because you have the COs through which you can get valuable information through IR spectroscopy. So the synthesis in this case, particularly for the NN donors, is fairly straightforward. As you see here, for the ones with carbene, it's a bit more involved, and the yields are not always that good, but you can make them. We have made all of these, characterized them, crystallized them, and so on and so forth. But for this purpose, these are the IR spectroscopic signatures of the corresponding rhenium complexes. You see the ligands here. So the rhenium tricarbonyl chloride is, of course, constant in every case. And if we just take the average CO stretching frequency, so this is just for comparison purposes, one should actually compare the individual CO bands. But if we take the average here, we actually get to the same conclusions. That's why, to keep things simple, I just show you the average CO stretching frequencies here. So as you see, for the carbene containing complex, this has the lowest value. And for the bitriazole containing complex, this has the highest value. So these data are telling us that this ligand is the best overall donor in the series. This one is the worst overall donor in the series. And bipyridine, as you see, is somewhere in between. So these bicarbenes are far better donors, overall donors, than bipyridine is. So this is one conclusion we can draw through these IR spectroscopic investigations. So again, this series, overall donor strength is the highest for this one, and the lowest for this one, and everything else is in between. And as you see, if as soon as we introduce a carbene, we drastically increase donor properties in these ligands. Then if we look at the electrochemical response, and for our purposes here, particularly the reduction, because reduction potentials as a first approximation can be correlated to acceptor properties of ligands. And if you compare these reduction potentials, what you see is this is the least negative for bipyridine. And again, for the bitriazole, this has the highest negative value. I mean, low and high with negative is, of course, always a problematic discussion, but the absolute value is the highest here, as you see. The bicarbene is also fairly high, and this pyridyl carbene is somewhere in between. So if we now compare all of these data, we can make the following conclusion, that in terms of acceptor properties, bipyridine is the best. The bitriazole is again the worst, and everything else is in between, with the pyridyl carbene also having a fairly good acceptor property. So now to just put this one on one, so if we compare donor properties, this is the best donor, that's the worst donor. This is again already quite good. If we compare acceptor properties, this is the best acceptor, that's the worst acceptor, and this is somewhere in between. So what does this mean for follow-up coordination chemistry and reactivity that you might want to perform? So this is what this means. Since this is the highest or the best donating ligand, if you want to stabilize relatively high oxidation states, this would be the ligand of choice. If you want to do, or if you want to pursue photochemical reactivity, so hemilability, photo-induced bond breaking, and so on, this will be the best ligand, because this is the worst donor and worst acceptor, so its binding to the metal is weak, and bond breaking will be facile in this case. And if you want to do reductive electrocatalysis, this is perhaps the best compromise, because you will still have low reduction potentials, because this is already a good acceptor, but you will have very strong bonds between the metal and the ligand, because this is also quite a good donor. So I will just show you 2-3 examples to drive home the point that this is actually the case. So now rhenium-1 carbonyl complexes, these are very hard to reduce reversibly, because if you oxidize these compounds, normally they decompose. But as you see, for this particular case with the bicarbene, we observe a completely reversible reduction in the cyclic voltammogram. And through spectroelectrochemical studies, we can actually prove that this oxidation is rhenium centered. So we are oxidizing rhenium 1 to rhenium 2 completely reversibly. As you see, IR, the CO bands shift by more than 100 wave numbers to higher values. And this large shift is a sign that we are actually oxidizing the metal center. And spin density calculations also show you that in the oxidized form, the spin is largely located on the rhenium center. So these data clearly prove that by using this bicarbene, which is a very strong donor, you can stabilize rhenium +2 oxidation state despite these carbonyl ligands. So this is usually, I think there is only one other example in the literature where you can have a reversible oxidation of a rhenium carbonyl complex from rhenium 1 to rhenium 2. So this clearly shows that these carbene ligands actually do the job that we expect them to do. Okay, then coming to these pyridyl carbenes. So very briefly, this work on CO2 reduction. As you see, this is the best performing complex that has isopropyl substituents here. And once we have a CO2 atmosphere, as you see, we get very large catalytic currents in this case. If you compare the scale here and the scale here, so this is the complex 3 that has this benzyl type of substituents here. So this catalyst is much worse compared to this one. And our hypothesis at the moment is that these benzyl substituents under reductive conditions are not stable. So you can have radical type of bond breaking, which kills the catalyst. So that's why with the isopropyl substituent, we have the best performing CO2 reduction catalyst in this case for making CO. So the product and so on has been confirmed through bulk electrolysis together with gas chromatography. And just to give you a feel for, excuse me, Faraday efficiency, as you see with the bipyridine ligand under these conditions that we performed the experiments, we get only 71% Faraday efficiency for CO, whereas with our ligand, which is the best performing one, we get near quantitative Faraday efficiency for generating CO from the corresponding metal complex. So now we are trying anchoring strategies and so on to actually heterogenize these catalysts and then see what this means in terms of recycling, product selectivity, and so on and so forth. Okay, let me briefly talk about H2 production, again using very similar ligands. So in this study, we used cobalt-3 complexes and made one complex with a carbene containing ligand that you see here, and two more with only nitrogen donating ligands. So these two complexes, they do nothing in terms of proton reduction. They just decompose if you put proton sources on them. So that's why I will not talk about these ones further. But this is quite interesting. So that's a cobalt-3 complex. The cation is not shown here in the ORTEP plot of the crystal structure. What is very interesting is if you take that metal complex and titrate in acetic acid, you actually get this S-formed catalytic waves for proton reduction, which means catalysis in this case is very fast and only kinetically controlled. So H2 we of course detected through mass spectrometry combined with bulk electrolysis, and this reaction through kinetic analysis we know is first order in catalyst and second order in proton. So we also have some ideas about how this mechanistically works. But for now, let me just briefly show you the Staffel plot where we plot the logarithm of turnover frequency versus overpotential for all well-defined homogeneous catalysis for catalyst for proton reduction that has been reported in the literature. At the time that we published this work, the red one is our compound and the other ones are various examples taken from the literature. So this had the lowest overpotential observed until that point, and I think this still holds. And at that lower potential, we already get fairly high turnover frequencies, as you see here. So there are, of course, other catalysts that have higher turnover frequencies than our catalyst has. But as you see, the over potential is more than double in this case. Yeah. So that's the compromise. So I think for our catalyst, this already is very, very good because the over potential is really, really low. And the turnover frequency is fairly high even at that low over potential. So again, we are trying to expand this work in various ways and means. Okay, so much for neutral carbenes and what you can do with them. Sorry, I just briefly tell you something about these chromium and molybdenum zero complexes also with carbenes, just to show you that you can generate carbene-based radicals. So as you see, reversible reduction processes for both the chromium and the molybdenum complex. Reduction is ligand centered, so carbene centered. Spin density tells you this. EPR, the simulation of EPR spectra also tells you this. And these were really the first examples of triazole illidine based radicals that were ever reported in the literature. To drive home the point about carbene stabilizing relatively high oxidation states. So again, chromium 0 with carbonyls to reversibly oxidize this to chromium 1. This is always difficult, but if you have a carbene donor, as you see, you can actually do this. And again, EPR and spin density will tell you that this is actually a metal-centered oxidation. So this again proves some of the points that I have told you in the last slides. IR spectroelectrochemistry again gives further proof that oxidation is metal-centered. Large shifts of the IR bands, and reduction is ligand-centered. Very small shift of the IR bands to lower energies in this case. Photochemically, what is interesting is if you take these complexes and shine laser light on them, you see a reactivity. So these are IR bands of the native complex. As you see, immediately after irradiation, you generate a new complex. What is intriguing is that this new complex actually goes back to the starting compound, as you see here. If you just let it stay, it goes back to the starting compound. So this is a reversible photochemical reactivity. So we are still trying to figure out what happens when you irradiate this, because normally one would expect CO release, and then this CO should go away and not come back again and coordinate. So we expect this is some kind of hemilabile behavior to get together with CO coordination on the free ligand and decoordination to the metal, but we still need experimental proof for this, which we are working on right now. But this is quite unusual that you get completely reversible bond breaking and bond making after laser irradiation in these kinds of complexes. Okay, so let me switch gears and now talk about cationic carbenes. So in this case, the first question we asked ourselves is, can we make cationic carbenes and change these strong donors to weak donors or strong acceptors? And can this be done reversibly? And can we then make electron rich carbenes, electron poor carbenes on demand, and then use this information in redox switchable catalysis? So why is redox switchable catalysis important? So if you have this kind of a system where the same ligand can be oxidized and reduced reversibly, then of course in this case you have an electron poor metal center, and in this case you have an electron rich metal center. So in principle, just by using a redox trigger, you should be able to perform two completely different and perhaps orthogonal catalysis. So one type of catalysis where you need an electron poor metal, another type where you need an electron rich metal, and in the best or in the simplest case, you should at least be able to switch on and off your catalytic activity. So let's see if this works. So to do that, we introduced this redox switch, ferrocene in this case. For gauging donor acceptor properties, we made these iridium-1 carbonyl complexes. You see crystal structures and so on here. Now, if you look at electrochemistry, if you have two ferrocenyl, you get two oxidations, as you would expect. If you have one ferrocenyl, you get only one oxidation. Then we did IR spectroelectrochemistry, and what you observe is per oxidation unit, you get a shift of about 12 wave numbers to stronger, to larger wave numbers, basically. So what does this mean in terms of Tolman electronic parameters that are used to characterize donor properties of these ligands? So as you see, the neutral ones, they are strongly donating, and they are actually better donors than N-heterocyclic carbenes. The one electron oxidized ones, they are less electron donating and in the regime of tricyclohexylphosphine. And then the two electron oxidized ones shown on the top, the L1C2 plus, these are actually as electron donating as triphenylphosphine. So we have quite a range through which we can tune electron donor properties. Now the question is, can this information be used in catalysis? So to do that, we made these gold complexes. The reason being the catalytic activity of gold 1 center, this is believed to correlate with Lewis acidity at the gold center. So let's see if this actually works. So again, for the gold complex with 1 ferrosinyl unit, you get 1 oxidation. You also see an irreversible reduction, which I'm not going to discuss now. So this oxidation is ferrosinyl centered. Spin density, as you see, clearly shows that as well. Now, if we look at chemical oxidation. So again, what we do electrochemically, we can do chemically by using this acetyl ferrocenium as an oxidizing agent, and UV-Vis data show you that you really generate the same species in both cases. So what you do electrochemically, you can also do chemically, and the oxidized compound, as you see here, also has a very different color. So what does this mean in terms of catalysis? So if we look at this cyclization reaction now, a benchmark reaction of converting alkynes to these dihydroxazoles, heterocycle synthesis. As you see, without any oxidizing agent, our gold compound is a lousy catalyst. But as soon as we introduce an oxidizing agent into the system, this gives almost quantitative conversion. So the concept that if you oxidize such a complex, the catalytic activity goes up, this definitely works. Can this also be made switchable? The answer is yes. And you see this in this particular slide. So if you add a reducing agent after adding an oxidizing agent, you basically stop the catalysis, you arrest it, you get a plateau in the conversion curve. And then if you add an oxidizing agent again, the catalytic activity shoots up again. So this is a redox switchable catalysis. And at the time that we reported this, the first example of a redox switchable catalysis based on a gold 1 complex. So since 2015, there have been several groups the world over that have used this concept to perform redox switchable catalysis on various types of gold complexes. So gold 1 complexes. So this is something we are very, very, very happy about. And then to show you what else you can do, so this is not restricted to dihydroxazole synthesis. You can use the same concept to make substituted furanes or substituted phenols, as you see here. So it's quite general. And then let me briefly introduce another gold 1 complex, now not based on ferrocene, but based on this cobaltocenium. Yeah, so I just want you to concentrate on the right hand side here. So these are of course dicationic carbenes, because each of the cobaltocenium brings in 1 positive charge. And at the time we published this was the first example of a dicationic carbene. Does not matter which carbene you take, and I think this still holds. And of course, since this is dicationic, this is expected to be very, very electron poor. The question is how electron poor, and here you see we have put this on a scale. So this is where the monocationic is, and that's where the dicationic is. And if you now compare which kind of ligands have such electron poor properties, you actually reach the regime of trifluorophosphines. So trifluorophosphines are one of the most electron poor phosphines that are known. And with our dicationic carbenes, we are in the same regime. So this should be very, very useful for performing catalysis where Lewis acidic metal centers are required. And this is exactly what we observe for our gold complex. So this does not need any additive at all. So this is a very potent catalyst on its own. As you see, in 2 hours, we get quantitative conversion. The only disadvantage is this is not redox switchable, because as soon as we try to reduce the cobaltocenium to cobaltocene, in that reaction mixture, our catalyst unfortunately decomposes, perhaps not unexpected, because in cobaltocene, the metal ligand bonds are not very strong. And if you have a catalytic mixture, then such a compound is probably expected to decompose. Now, I would like to conclude the cationic part or cationic carbene part by showing you a last example. So this is the gold 1 complex I was talking about in the last 2 slides. What we then observed is that you can actually take this complex, dissolve it in aqua regia, and make the corresponding gold 3 complex. Yeah? So this is, I think, something that no one would have expected, that you can actually do organometallic chemistry in aqua regia, which is known to be a very, very harsh solvent. So this compound, it survives. We get about 70% yield of the corresponding gold 3 complex. The chlorides, of course, come from aqua regia. You see the crystal structure here. What is also interesting is now this gold 3 complex is also catalytically active with the same substrate. We need a different solvent because of solubility issues, but the gold 3 complex delivers a completely different isomer of the product compared to what we saw with the gold 1 complex. Yeah? So this is also a nice example where by using gold 3 with exactly the same ligand, you get a completely different product selectivity in this case. And the fact that you can use aqua regia to oxidize an organometallic complex, I think this is quite unique, and this concept has already been used for 3-4 other works since we published this first result at the end of 2019. Okay, so much for cationic mesoionic carbenes. So in the third and the last part, I would like to talk about anionic mesoionic carbenes, and these would be based on a borate backbone. So you see some examples from the literature, not based on triazoles or triazolium salts, but based on imidazolium. So Fellhammer was the first one who reported on imidazole illidane type carbenes based on a borate backbone. These compounds were then used by several other groups to generate metal complexes with very unique properties. You see some reactivity studies here. And for this particular part of the talk, secondary coordination sphere interactions will be very important. So I just briefly mentioned this here. So usually in coordination or organometallic chemistry, one would try to tune properties at the metal center through the first coordination sphere. But of course, this does not have to be like this. In biological systems, this is very well known that the secondary coordination sphere plays a very, very important role. For example, in this heme type protein or hemoglobin, to be precise, dioxygen activation actually works that well because you have this secondary interaction to an imidazolium group in the secondary coordination sphere. So you can take inspiration from nature in this case, and of course it is also well known in coordination chemistry that the secondary coordination sphere in the best case can have a very strong influence on properties and reactivity of the metal center, and I will show you that this is also the case for our complexes through non-covalent interactions. Okay, but first, a bit on ligand synthesis. So basically, we are talking about these two ligands. Both are boron based. Both are anionic. I mean, these are the precursors. Of course, we have to deprotonate these twice to make the carbenes. And as you see, the backbone is different. So we have cyclohexyl here and phenyl here, but the first coordination sphere will be identical. So let us see what kind of influence this has on the properties of the metal complexes. So our aim was to make a cobalt carbene complex with a bicarbene donor. So what we observed during the reaction is if you try to metallate that ligand, what you actually generate is not the product that we expected, but these complexes where either one part of the ligand is isomerized that you see here, or both are isomerized that you see on the extreme right. So these have been characterized by X-ray crystallography, so there is no doubt about the nature of these complexes, and the cobalt centers are perfectly square planar in both cases, fairly unusual with bidentate ligands. So we are 100% sure that the complex that we wanted to make exists in solution. So the first one showed here, but we have not been able to isolate that complex as yet, but we hope we will be able to do this in the next months. So then we asked ourselves the question, is cobalt necessary for this isomerization reaction? The answer is no. So here you see a deprotonation with the lithium containing base in the absence of a cobalt salt. And in this case, we also get the isomerized product as NMR shows you. So basically deprotonation is spontaneous. That's the spectrum after 1 hour at minus 30 degrees centigrade. But as you warm this up, the initially formed species gets converted into a different species, and the NMR of that species actually matches with crystals that we isolate out of this reaction. So the crystal structure is shown in the next slide. This is a bit slow now, just 1 minute. Yes, so that's the crystal structure. So a dilithium compound is isolated in this case. And as you see, the ligand backbone is isomerized. So this clearly proves that the deprotonation does not require, the isomerization does not require cobalt. and through temperature, you can actually get to quantitative yields of the isomerized compounds. So then we modified the synthesis of the metal complex a bit, used a slightly high temperature, 50 degrees centigrade, and then we almost quantitatively isolate the isomerized cobalt-2 complex, which is perfectly square planar. So this, of course, reminds one of cobalt porphyrines. So that's the compound. And cobalt porphyrines, cobalt-2 porphyrines are square planar, and they are known to undergo various intriguing reactivities with dioxygen, but also with pyridine as a donor. So in this case, we were very surprised that this complex does not react with any of these external substrates. So then we asked ourselves the question, why is it like this? And the first step in that direction was to perform EPR spectroscopic investigation. So in this case, single crystal, without going into the details, you can do these orientation dependent measurements, make these plots, make a matrix out of this diagonalized, and then you will get the three principal G values. Now, if we take those G values and compare them to what is known for cobalt porphyrin, so as you see here on top, 4 coordinated square planar cobalt porphyrin, and this is cobalt porphyrin with axial ligands. So the G values that we obtain for our metal complex, this is actually much closer to the G values obtained for porphyrin cobalt complexes with axial donors. So then we looked carefully at the crystal structure after we also had the calculations, because in the calculations, you clearly see there is some kind of additional interaction to the cobalt center. And if you then look carefully at the crystal structure, you see this is, of course, to the first coordination sphere, this is square planar, but the CH atoms of the cyclohexyl substituents, they really form these directed agostic interactions that actually function like axial ligands, and that's what is shifting the G values. So this, even though it appears as a square planar, for all practical purposes, this is a pseudo-octahedral metal complex, and hence all kinds of reactivity is blocked in this case. So then we thought, if this is the case, let's change the backbone and see what happens. So we changed the backbone from cyclohexyl to phenyl, as you see here. And the first surprise, or maybe not a surprise, this is what you would actually expect, is that this complex is now not square planar anymore, like with the cyclohexyl substituents, but tetrahedral. So this is also high spin and not low spin like in the previous case. So this is high spin cobalt-2 tetrahedral. So geometry, spin state, and so both geometry and spin state is controlled by the secondary coordination sphere in this case. Then we wanted to check if this complex would show reactivity, and it does. It reacts with dioxygen to give you a superoxide species that can be characterized through EPR spectroscopy. It also reacts with pyridine to give you a 5-coordinated low-spin cobalt-2 complex. You see EPR here and the crystal structure here. In this case, we could also isolate the corresponding metal complex. This is only result from in situ experiments. So then to summarize, you see, just by changing the secondary coordination sphere, we can change coordination geometry and spin state from square planar to tetrahedral and low spin to high spin. The color of the compounds is, of course, different. Since this is pseudo-octahedral, this does not react with any external substrates. This reacts with dioxygen to give you the superoxide species, and with pyridine to give you a square pyramidal cobalt-2 complex. Okay, so let me conclude. I hope I could show you, so the first part I did not talk about today, of course, but I hope I could show you that you can use these mesoionic carbines made through the click methods for small molecule activation and bioinspired catalysis, for doing redox switchable catalysis, that was the cationic carbene part. And finally, you can make anionic carbines and see or observe additional interesting reactivity with these metal complexes. So for me, a big take-home message, because I originally come from a completely different field, is that if you really combine various aspects of chemistry, you then generate results that you would never expect if you just focused on one side of the story. Let me thank the people who actually did this work. So the ones that are marked here in red, maroon, whatsoever, are the people that have done or are doing this work in our labs at the moment. So I'm also very, very proud of people who have left the group. Here you see a complete list. So they have either gone on to make good careers in academics or have big industry jobs. And of course, I hope that the current members will follow suit. A bunch of funding agencies for very generously funding our research over the years now. And of course, a host of collaborators without whom many of these work would not have been possible. Several people in India, so Professor Lahiri is actually my mentor from my master thesis times, but somehow we managed to be in touch for 20 years now and also collaborate. And then these other people with whom I started independent collaborations in the last 4 to 10 years or so. And then, of course, people from various other parts of the world. So I thank you again for listening to this presentation. Thank you very much for thinking about me and inviting me to this conference. And I would be very happy to take any questions. Thank you.
Thank you, sir. So we have time for a few questions. So any questions in the chat box? Any questions in the live stream? I hope I can initiate the discussion and then questions will come on. So you have talked about 3 different types of carbines: neutral one, and the cationic and anionic one. And in the neutral one, you have tried like a small molecule activation, especially with the CO2 reduction. The same kind of thing can we do with these ionic ones also? Can we
So
try?
with the cationic ones, I would say it will be difficult because, as you would know, the first activation step in CO2 reduction, irrespective of how you do this, is of course a reductive activation. But I'm quite sure that with these anionic carbines, this will work well if one finds the current system, and there you might also see some nice interplay to the boron atom as well.
Okay. One more question, sir. With regard to the secondary coordination sphere, which you were talking, which plays an important role, especially in the anionic one. So in the case of the CO2 reduction part, like which you have mentioned in the neutral one, is there any such effects possible in that case?
Yes.
Because
So
yeah, because mostly the this capture part, CO2 in capture part of the metal is important. In that case, the secondary coordination sphere will play an important role. Have you observed anything like that?
So in terms of capture, what we have observed is that if you have let's say acidic protons in the vicinity, this becomes more facile. So this is something you already mentioned, and this works. What is equally important in terms of the secondary coordination sphere is so we have some preliminary data, but I think more importantly, there is also several reports in the literature that shows this, that you know, in the vicinity of the place where the CO2 is coordinated, so around the CO2, if you either have proton sources or simply positive charges, because this electrostatics also seems to play a very important role, then the parameters for electrocatalysis that you get, so these overpotential turnover frequencies and so on, these improve massively. And I think one of the recent results in that direction is if instead of introducing a proton source, you simply introduce a positive charge, you can actually reduce overpotential and at the same time increase turnover frequency. So this is something that usually never happens. So there, I'm sure there is ample scope to tune such things in that direction.
In the as you mentioned, like it will reduce the over potential but increase the turnover frequency. If is that because there is a possibility of low concentration like CO2 reduction, which is a new strategy in CO2 reduction. So if it can capture CO2 due to the positive charge, maybe the TON will also get enhanced.
Yes, 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 yes.
Yes, sir. Like any questions? Any questions from the audience in the auditorium? Okay. So, so we had a very interesting session by Professor Biprajit, where he introduced us the possibility of using meso-ionic carbenes, and he had introduced many new possibilities of meso-ionic carbenes, especially in catalysis, then optically switchable materials, and in some organic conversions. And he also showed some best results where rhenium is used in meso-ionic as with meso-ionic carbenes as ligand, where they are observing very high turnover numbers with lower over potential. So with this, I thank Professor Biprajit Sarkar for the wonderful lecture. I hope the students are really motivated by his talk, and we wish to have in the coming MATCON also, sir. Thank you so much, sir. Thank you so much.
Thank you. Thank you very much for having me. Thank you.